Hello, everyone. It is an honor for me to introduce to you Amit Singh, who works on macOS 10 technologies for Google. We met some time ago after both his team and my team independently ported Linux to the Intel Macs. So that was an interesting experience to meet him afterwards. Some time ago he invited me to Google to speak about hacking the Xbox, so I'm now very proud that he can be here in Berlin and speak about OS 10 hacking and the TPM. Also thank you to Angelo Laub who motivated him to come. So please welcome Amit.
Thank you. Good afternoon, and thank you very much. Thank you for inviting me, and thank you for coming here to this talk. This is a talk about the so-called DRM, or software protection, whatever you might want to call it, in the Intel version of macOS 10. It's also a talk about this little piece of hardware they call the TPM, the Trusted Platform Module. And in a way, it's I'd rather be using these things as excuses to take a little journey through the internals of macOS 10, kind of looking at how some parts of the system work so that we can understand what's exactly going on in the context of these things. Apple is a unique OS vendor. They're unique not because they have like a fanatic fan base or, well, that's one reason. First of all, there are not many OS vendors left. And Apple has been dying for a long time. They just don't die. They always come back. But if you look at the history of Apple's operating systems, if you just look at the number of systems they have shipped and the number of systems they have tried to ship, it's like 3 dozen. Who has done that? Microsoft hasn't done that. Sun hasn't done that. No other OS vendor has done that. So I'm not saying that's a great thing, that you keep trying and you keep churning one thing after another and then it's forgotten. But at least they do that. So Apple gave the industry kind of a shock last year when they announced that they were giving up their long-standing relationship with the PowerPC and are going to start dating Intel. And well, it made lots of people unhappy. It made me unhappy because I really like the big Indian. It's a big thing for me, and for a while I just couldn't reverse engineer anything because I'm like, what the hell is this? Why are all the bytes backwards? But at the same time, it made a lot of people happy. It made those people happy who wanted to use something that Apple made, who wanted to use OS 10 but who didn't want to buy into Apple hardware. It also made those people happy who wanted to buy Apple hardware but they wanted to run all kinds of operating systems on the machines. But it wasn't going to be so easy. I mean, if you expected that Apple's going to give all this to you on a platter, then you're mistaken. They're a company. There were 2 important obstacles to begin with. One was that Apple chose kind of expectedly not to go with the BIOS. So they had a new firmware, which had been languishing in Intel's labs for a long time. Intel wanted people to use EFI a long, long time ago. And it almost died before Apple took it up, and now it's cool again. I actually talked to the person who's supposedly, I mean, who's primarily the inventor of EFI, and talking to him a few years before and talking to him now, it's like he's like a new person. And so yes, since it doesn't have the BIOS, you at least have to do some work to do either of these 2 things, running another system on Apple hardware or running OS 10 on non-Apple hardware. The very first Intel Macs that were revealed to the public, I'm talking about the developer preview machines. It was found that they had these evil TPMs in them. And so did the first shipping Macs. So there was this whole mystery to the whole thing that what is Apple doing with the TPMs and how does this whole picture fit in. And so I've done work on and off at TPMs. I used to work at IBM Research, and probably most of you know that IBM was a big player in at least the TCG specifications, and IBM were probably the first vendor to actually mass ship these things. But even then, it was kind of strange because they were shipping all the NetVista computers, all the laptops and the desktops with TPMs in them. Before that, there was some pre-version of the TPM, but nobody was using them for anything. And companies don't like that. They don't like to ship stuff that's not used and nobody knows what to do with it. And Microsoft is to be blamed for that, because Microsoft wanted to do their own thing with Palladium. And when people hear TPM, they equate it to Palladium, and they just don't like it. And this is kind of how they see it. This is how it is. So anyway, without taking sides in this yet, I mean, I don't think I'm going to take sides even at the end. So, but the combination of these factors kind of put a little cloud over the excitement of the people who wanted to use their new Macs for all kinds of stuff. Not so easy. Taking a moment to look at it from Apple's standpoint. So what is Apple's most important asset? I mean, as an outsider, I think it's the users. Have you ever argued with an Apple user? I mean, I've come close to pulling my hair out at something that can be proven. It's like logical. It's logical in CS terms, and you tell them this is how it is. And they're saying, no, who cares? But anyway, so regardless of what Apple did with their new systems, DRM-wise, software protection-wise, licensing-wise, serial number-wise, whatever they did, they had to keep the users happy. I think that's really important for Apple, and they realize that. But the other thing is, if they, like with the PowerPC, Apple had a long run that it's like an esoteric platform. It's not. You can't just go out and buy a PowerPC machine. So Apple didn't really have to care about clone makers again. They didn't have to worry about people stealing. What are they going to run it on? But that would be a real problem now. So regardless of what Apple engineers think, Apple has to be able to sue people who, if you want to sell clones or something. And for that to happen, it has to be at least a little bit non-trivial to take their system and run it somewhere else. Because if you just pop the CD in and it works, then it's not going to hold water in a court of law. So they had to keep the lawyers happy. And engineers and lawyers don't really mix. I mean, with apologies to engineers and lawyers who might be present here. So Apple had a kind of a difficult problem on their hands. How much money and resources do they want to put in? So with that, let's make a context switch here. And in order to understand what comes afterwards, let's see if we can understand how virtual memory works in Mac OS X in like 5 minutes. So everybody knows that Mac OS X uses Mach. Everybody knows they don't use it as a microkernel. Everybody hopefully also knows that Mach was never used as a microkernel outside of a lab. But when people hear Mach, they say microkernel, which is really unfortunate. What's also interesting is that OS X VM subsystem is based on, it is the Mach VM subsystem, which is also the parent of the FreeBSD VM subsystem. And interestingly enough, when Sun was overhauling their VM subsystem at some point when going from Sun OS to Solaris or whatever, they independently came up with a VM subsystem that actually very close to Mach's VM subsystem. So in general, it seems like a good idea because all these smart people are coming up with pretty much the same design. So when you think of an OS X app, it's like, this is a stereotypical OS X app. It's kind of nice and candy-like, lots of interface elements. It's doing something very complicated in a very simple way. But in truth, when it's running as a bunch of threads. And actually, each of these is a mock thread. Now, I say mock thread because and all these mock threads, they live in a mock task. So why do I say mock thread? I say mock thread because it actually kind of looks like this. So the thing that eventually runs in the kernel is a mock thread. But depending on what you're programming, and you're using Cocoa or you're using Carbon or Java or something else, depending on that, you would deal with your own thread or process abstraction. But in user space, everything eventually boils down to a POSIX thread or a pthread, which has a one-to-one mapping with a mock thread in the kernel. If you have time left at the very end, please remind me. I want to show you a very interesting demo that kind of uses some of this thread stuff, but it's unrelated to the talk, so it's optional. So we have all these threads, and but what about processes? Because we know how close to Unix OS X is. Apple hypes that up a lot, and you can run the PS command and you can see process IDs, you can suspend processes, you can send them signals, you can do pretty much the same stuff you can do on a generic Unix system. So if we have all these tasks and threads, what is a process then? So that picture looks like this. What you see as a process and what you see as a process ID is essentially just some syntactic glue on top of a mock thread, because the Unix side has to be happy. The rest is kind of what I showed in the earlier slide, that you have pthread in user space, they have their own stacks, there's a one-to-one mapping, you have mock thread in the kernel, they have their own kernel stack. All of them belong to this mock task. And the task is really this giant container which contains what actually concerns us here, the virtual memory of your program. So, okay, let's focus on the virtual memory aspect. So we'll just look at 32-bit processes because it's the same without making it more complex. So what is an address space? It's just a range of numbers from 0 to 4 gig. The name for address space in Mach is a VM map. I think it's VM map in many operating systems. There's also a physical map which contains information as to which of the virtual memory is currently physically resident. And the physical map is the only machine-dependent module. So, unless you're crazy or you've written some weird program, you're not going to be using all 4 gigs of memory. So, typically memory is sparsely populated, which means you have these blue regions that you allocated or were allocated on your behalf by the system. And a further subset of that would be resident. The rest may not be resident. So if the whole thing is a VM map, then one of these blue things is a VM map entry. And so VM map entry it's just a contiguous range of addresses with the same properties. That's all it is. When I say properties, I mean the same sharing, the same inheritance, the same protection. And in fact, you have a double linked list of all these VM map entries. And in fact, if you go and change, some address range in the middle, you use mprotect or something else, then it's going to actually split it into 2 or 3 based on where you were. So, okay, so far so good. Then we have something called a VM object. This is something that has information about that when you actually touch this memory, when you access it, where it's going to come from. We'll look at VM object in a second, but every VM map entry has an association with one VM object. There could be sharing because nobody prevents you from mapping the same memory in multiple virtual addresses. So you could have a VM object that's shared between many things. Looking at a VM object further, it can be distilled to these 3 things. VM pages is just a queue of pages that are currently resident. And so this is physical, this lives in physical memory. So your VM object knows what is in memory and what's not in memory. Shadow object is actually another VM object. If it gets weird or complicated, tell me. I hope not. So shadow object is another VM object which gets created when you do copy and writing. So to begin with, you have one VM object. And let's say you copy and write share it with somebody else. So to begin with, there's just one VM object, and somebody actually writes to it. So what the kernel will do, it will create a shadow object, which will contain the pages that you just modified. And it'll attach them such that the person who modified, when the kernel is accessing things on their behalf, first you will see in the shadow object to see if there's a new, it's basically common sense stuff. And as you keep writing more, you will have these chains of these shadow objects, which can collapse if necessary. And then we have this interesting thing called a memory object, which is really the portal to where the memory comes from. And a memory object is implemented as a mock port. So a quick aside on mock ports. I think the simplest way to understand them, and it's kind of important to understand them because they underlie all mock IPC, and IPC underlies all mock operation, and mock underlies OS 10. A mock port is kind of like a Unix, like a BSD socket, except that it's not really for networking. It's optimized for the local case. So there's a message queue in the kernel, and you can do asynchronous message sending and receiving. But the special property is that there's only one task, technically any thread within the task can receive messages on a given mock port. And this property is known as that the task has received writes to this port. But you can have multiple senders. So why this mock message thing and this port thing is important and actually really, really useful for people like us is because all system activity happens through these things. For example, your window manager. If you're talking bottom line, your window manager represents each window as a mock port. So if you wanted to do some funky stuff with a window, at some level you were talking to a mock port. And then the other kind of interesting property is that the kernel also is a task. And mock APIs do not really distinguish between, when you do IPC, it doesn't matter if you're sending it to the kernel or user, because the kernel is the arbiter. But you can modify the kernel like you would modify a user task. So for example, if I want to allocate some memory in the kernel, I can do it exactly the same way as I would do it in user space. If I want to set the instruction pointer of a given thread in the kernel to something I want, given the right privileges, I can do that very easily, but exactly the same way I would do it in user space. So this uniformity is both good and bad, but for most of the stuff I like to do, it's actually very good. So given that we know what a mock port is, memory object is just a mock port. So I told you about receive writes and send writes. So who owns the receive write to this port? Well, that's the pager. And pager is just what it sounds like to be. Pager is the guy who actually gets the memory from wherever it lives. So now let's look at the memory object in more detail. I think this picture sums it up. So where could memory come from? Well, it could come from many places, right? It could come from a file system. If you mmap files like all dynamic shared libraries and whatnot, they're memory mapped. So they can come from the file system, and that's handled by what's called a vnode pager in macOS 10. Memory could come from a device like a frame buffer. That kind of memory is handled by the device pager. Memory could also come from nowhere, because if you malloc, it comes from nowhere. So that's anonymous memory, but when you want to write it out, it has to go somewhere. So normally it goes to the swap space. So the pager that handles that is the default pager. So macOS 10 has at least 3 types of pagers, the ones that I just mentioned. Now why do I say at least? Well, before I answer that, in this picture you can do something like this. Meaning you can just interpose a new pager, and you can start like siphoning memory or feeding memory if you want. pretty much using interfaces. So why this thing is kind of cool, because you're not really hacking anything if you're using interfaces. Like Apple doesn't want you to use the interface and they're not documented, but still, all this can be done with just the supported stuff. So given this picture, one of the things Apple does is what's called Apple protected binaries. So this is one thing I really like about Apple, which is that they're very pragmatic. If they're solving a problem, so they have as good engineers as anybody else. So somehow they know, for the most part, where to draw the line. They're not going to solve the problem until, like those who are working on it like die of frustration, and it's like you have to go to the academic edge case that it cannot be broken in any circumstances to solve it until then. They don't do that. They actually solve it for most of their users. And so this is a good example of that. So if you look at the Finder, for example, the Finder binary on your system, it's an Apple protected binary. What that means is it's just encrypted. And we talked about AES encryption a little before. It's encrypted using AES. And yeah, I mean, there's got to be a symmetric key somewhere. So with the pager picture, all this VM knowledge that we just gained, essentially this is what they do. So you have an encrypted binary which lives on disk. When you're reading, it goes through the vNode pager as it normally would. The numbers are kind of backwards, actually, if I start from here, but it's okay. So they just set a special bit in the Mako header of the binary which says, hey, this is an Apple protected binary. You can clean that bit and you'll see that it just said false. So it'll go to the pager. The exact vsystem call implementation identifies this bit, and what would normally happen is that the first page is not encrypted. Actually, the first 3 pages are not, because they got to identify what's going on. So normally, you would start mapping pages in as you try to execute a binary. So the moment they see that it's a protected binary, all they do is that they instantiate something called an Apple Protect pager, and they swap the memory object port so that the original VM object sees the new one, and this guy has the old one. Very simple. I mean, there's no tricks here. So all that's happening is that this guy reads protected, encrypted data from the file system. It decrypts on the fly. And it's a trivial pager because this stuff is never going to be paged out. You're not going to write to it. You don't have the keys. You shouldn't write to it. So that's all. I mean, that's one of the things they do. And oh yeah, there's got to be keys somewhere. So yeah, so there's keys somewhere, and the keys come from somewhere, and that's how it works. And while we're on the topic of VM, before we switch context again, there's this interesting experiment you can do which actually highlights multiple things at the same time. So what are you doing here? You're printing like some address as a string from the end of your address space, minus 16 times, so like last few pages. And if you compile it and run it, so what do you see? So what is this thing doing in your address space, first of all? And I'm talking about every process's address space. Like you can write a new program and you'll see it there too. Well, first of all, this is a feature. Well, not the poem. I'm talking about the fact that things are mapped in your address space. The feature is that, in there, like, have you ever wondered, I don't know if you've experienced it yourself, but I've certainly heard a lot of Apple users say that, Apple has this wonderful way of making every release faster on the same hardware. So there's no magic. They must be doing something right. So they do some things which actually help. Some other things don't help. I think the users are just hallucinating. But no, but they do some things that actually help. And one of the things is that Actually, we don't have to go into that. That's a whole new topic. But the way this feature works is that they map shared libraries into the same addresses, virtual addresses in every process. So, which means that C library is going to be mapped into the exact same virtual addresses in every process. Well, forget about C library. Let's say it's some weird, like, funky Apple library that nobody uses, but that's going to be mapped into the same space too. So what if you need that virtual memory and you're not even using that library? Well, tough luck. But it worked for the most part. I haven't heard people complain that I ran out of virtual address space. I really wanted that memory and couldn't get it. Okay, so in that pager picture, much of the decryption code lives in a kernel extension called Don't Steal macOS 10. And the poem is put there by that extension. So this is like assault. Like they verify that everything is fine and dandy. And if it is, they say, let's just put it in every address space at this address. And it's kind of like a little flag that says, it's no big deal, which says everything is okay. You can put it there yourself. So let's switch context again. I think when I was going through the past year's proceedings or the talks that were held here, I think most people should know what these are, how they work, what capabilities do they have. So I'll try not to talk too much about these things because I don't want to be redundant. But for what it's worth, 20 million of these shipped last year. And it's expected that by 2010, there will be about 250 million of these deployed. So whatever these things are, good or bad, they're out there. And like I said earlier, Microsoft's Palladium had a lot of bad vibes to it, and it sounded quite draconian. And they were not even using the TPM, for God's sake. They were using their own chip. But the TPM actually got a lot of, and they're valid concerns. Not all of it is invalid. But, so first of all, so it's in many Intel Macs. It's not in all Intel Macs. We'll come to that later. But in machines that do have this, it just sits on the LPC bus. It was actually not required to be on the LPC bus earlier, but the new specification of the TPM 1.2, it requires it to be on the LPC bus. I understand most people know but actually that's not even important. Now, what's inside it? I think the easiest way to think of it is that it's like a smart card, except you carry a smart card and this is on your motherboard. And in fact, if you see what chipset is inside, what embedded stuff it's running, it's actually running the same stuff as a smart card would, except it's like when the company who manufactures this also makes the smart card, so there's a small production difference. But it's running a lot of the same things a smart card would. Stuff like this. So there's a microcontroller. Which thing doesn't have a microcontroller? There's a few types of memory, both volatile and non-volatile. And there are some functional components, lots of cryptographic stuff, some of which it exports, some of which it does not export. For example, some people I've talked to, they kind of think that it's like a crypto accelerator. It's not, and that's for good reason. It's because they want it to be cheap and they want to be able to export it. So this is not a crypto accelerator. It does do both symmetric and asymmetric cryptography, but the symmetric stuff is internal only. It's not even exposed. So we will see some of these components later on. But so that was like an internal view. But from a programming standpoint, what can you do with it? So if you're a programmer who wants to access this, well, you can use the functional units to do some kind of signatures. You can get like really nice random numbers. You can get like monotonic counters. It has a bunch of keys. We will come to the stuff that actually matters to us in this talk. But it actually has storage now that you can use for anything you want. It's very small, but it has some storage. And it has a bunch of registers that can contain SHA and hashes of whatever you want. If it sounds vague, let's get to it in a moment. So given this, what do you do with it? Well, so it has some nice properties. One of them being, actually, I think some of them can be, the really important ones can be distilled to this, that let's say you create an RSA key pair. The private key will not leave the chip unwrapped. Again, it's kind of like a smart card. The public key is yours. So you can do RSA signatures using this, but you can't actually take the key out and put it somewhere else. Well, technically you can, but you have to create the key with those properties. But let's say we don't want that. So it gives you like a decent way to validate the identity of the machine. So think about, I want to use SSH to go from here to there, and I want to use public key with SSH. So normally what you do is you might use SSH keygen, you create a public key and a private key, you leave the private key here, you copy the public key to the server, and then you log in. But you can replicate these keys and you can put wherever you want, and even then, the protocol, when it does the key exchange, well, you know that, yeah, probably the right keys were used, barring any bugs in the system, but you don't know if this machine was used. So if for some reason you want to make sure that this machine was used, this can help. The stereotypical use case which the TCG wants to, the body behind this wants to advertise is that you put this chip in a system, you make the BIOS or the firmware aware of this, and when you boot the system, you put this tiny little piece of code which even runs before the BIOS. And you kind of implicitly trust this code because the manufacturer put in there, and it's supposed to be secure and all, and you trust the manufacturer. So this code will checksum the BIOS, for example, and it can put the checksum in one of these registers. So this thing has 24 registers. So it'll just do a SHA-1 hash of the thing and put it in the register. And another property of this hashing is that you can actually set these registers to a given value. You only provide them with a hash. And what the TPM will do internally is that it'll concatenate this new hash you gave them with the existing value, and then it'll do a SHA-1 of that, and it'll keep that in there. So you indirectly set it. You don't set it to a given value, and you can't like roll back to another value. So this way, the BIOS could check some the option ROMs. It could check some CPU microcode updates. It could check some the bootloader. The bootloader could then check some, the second stage bootloader, so on and so forth. You could check from the kernel, and then you end up in what they think is a secure, authenticated boot. Well, you check some of the binary that you loaded, that's one thing, but I mean, once you check some and once it's running, so it looks like they kind of try to hand wave some of these issues, and there's plenty of material on this, so I will only deal with what actually matters in this talk. So I showed those keys in the picture because we were talking about Mac OS X and the TPM. So yeah, so this is in the Intel Macs, and they're using encrypted binaries, and they don't allow you to run OS X on non-Apple hardware easily. So where does the TPM fit in that picture? The answer is nowhere. And yeah, so this is really a phantom menace. I mean, so much of build up for nothing. Unfortunately, that's the truth. Okay, so it's another interesting question. Did they think about this, though? I mean, were they thinking of using the TPM for, well, I don't know if they were or they were not, but have you ever looked at what it would take to create a system that does what they would have wanted? I mean, it can be summed up to the thing that you may have the TPM, but your system is not, I mean, there's no mandatory access control. There's no Palladium. So what are you going to do? I mean, yes, you can check some things as they load into memory, but then when you have supervisor access, you can bypass whatever you want still. So there's an important subtlety here that in the absence of mandatory access control, whatever you do here is just fluff, because eventually it all boils down to that normally how you would crack something else, like a software DRM, you would be able to do it here too. Would it be harder? Well, yes, in some cases. But, and it's not even a new concept. There was this thing called the Anderson Report in 1972, which I believe were the first thing to talk about the concept of a reference monitor. And they were talking about these problems even then, that how do you trust your systems? What is a trusted system? How do I know that it's not being compromised? And it turned out that, and people even then realized that, well, as long as you have this architecture where you have all these user programs and you have this really nice user kernel boundary which doesn't let you do any nonsense, and there's all the memories protected between processes and other processes and the kernel. But once you're in the kernel, you can do anything you want. And yes, you can have lots of mechanisms that may tell you, I mean, that may be used to make it really hard for you to do that. But if you are the kernel, you can even rewrite some of those mechanisms. So it just becomes more difficult. It doesn't become impossible. Let's context switch once again. So Mac OS X has this hardware. I mean, Apple computers have this hardware. And it's not used. So we want to use it. How do we use it? Well, it's really well supported on Linux, actually. And it's the same chip. So there's a Linux driver for this TPM. It's the Infineon TPM. And IBM has been working a lot in this area. They even wrote this huge, like 100,000 line software stack for this thing, which is open source and available on Linux. And you can do a bunch of secure storage, all kinds of, you can do like a PKCS store that uses the TPM. You can use it with OpenSSL. You can do a whole lot of things. Many of them are interesting. But let's say we want to use them on OS X. So A, we don't want to rewrite that whole stuff. And B, ideally, we don't even want to rewrite the driver because it's not really new stuff. It's just, we just want the functionality. At least that's my thinking. So the Frankenstein nature of Mac OS X comes to our aid here. So when I say Frankenstein, it is Unix, it is Mach, it has BSD-style devices, it has dev nodes. It has an almost POSIX-compliant suite of libraries. But is this stuff really that, I mean, is it really that nice that you can just port whatever you want to it? So here's what I did. I don't want to program more than necessary. So I looked at the Linux driver, and it looks like a very well-written and small piece of code that essentially drives. So when you talk to the TPM, I mean, you access this thing on the LPC bus kind of like you access ISA devices, the legacy-style stuff. And there's a couple of registers, and you just do port memory mapped I/O to these things, and then you drive this whole thing. So I reckon that if I can write a driver for OS X that essentially re-implements in-bees and out-bees, so I don't even want to rewrite the Linux code. I just want to take it and drop it in and have it run. But it wants in-bees and out-bees. So if I can provide with Linux semantic style in-bees and out-bees, and I can give it a dev TPM-like device, then driver will work. It will have the same user space interface, and hopefully this giant suite of Linux software will also work. So one of the key differences between OS X and other types of Unix is its driver library. And this is something that they inherited from NextStep. And the idea was that with their visual tools like the precursor to Cocoa and whatever, they made it quite easy to write most types of applications. And at some point, some people decided that, well, but writing device drivers, why is it black magic? Because, well, for one thing, you're in the kernel, you can't make mistakes. or you should make mistakes. But still, there are so many things to be aware of, like synchronous stuff happening, call-outs happening, timers, blah, blah, blah. It's like, it's a madhouse. So how do you do something that's decently documented, and you don't have to worry about thinking about the nuances of this system. You can just care about your driver logic. So well, what they did was that they said, let's just make a driver toolkit that shields the user from the rest of the kernel. And like they have all these Objective-C interfaces, we will just give C++, embedded C++ interfaces in the kernel. And so much so that it actually works quite well. It really, really works quite well, whether you're writing a driver or you're hacking something. I'll give you an example. Let's say that you have you got this lump of Apple firmware from somewhere. You know, like it's an open firmware image that you want to update your machine with, or it's an EFI image that you want to update your machine with. So there's a kernel driver for this thing, and it actually represents the non-volatile memory of the firmware as a file system, or as a partition table. Now, what I could do is that I could write a driver that could inherit from one of these classes. And well, there's a function that says, read from this partition. There's a function that says write to this partition. And I don't even have to actually worry about anything. I can just instantiate it, instantiate myself, and I get the benefit of everything that's on top of me. So you can do things like these. So it was quite trivial to write this driver. And did it work? What happened when I lumped this whole piece of Linux toolkit on top? Well, not initially. That's because macOS 10 is POSIX compliant, but almost. They do some weird things, and some of it is intentional, some of it is not. For example, they support, let's talk about like System 5 IPC or System 5 shared memory or semaphores or something like that. Well, they do support it because you can see the functions in the C library. Well, sometimes they forget a function. So like the function to delete it is there, the function to wait on it is there, but there's no function to create it, for example. So they do things like that somehow. In one case, I found that one of the functions was a stub. So I'm expecting to actually like block on it, it just falls through. And have you tried debugging stuff like that? Because like there must be a problem with what I'm doing. But so they do stuff like that. But once you get over that stuff, which is not more than 10, 20 lines of code in this 100,000 lines I'm talking about, the whole thing does work. And so this is kind of a nice example of taking both a kernel driver from Linux and a software stack from Linux and just recompiling it with the right glue added, and it does seem to work. And that makes for some interesting experimentation. And I'll show you a few experiments. So no GUIs for me. I have the TPM driver loaded in Linux style. Let's go look at it. I'm expecting a question here. No question, huh? There's no macOS 10 users here? Okay. We'll come to that later. Okay, so this is a proc file system representation of the TPM, very Linux-like, very Solaris-like. No, not Solaris-like. Solaris uses it for actual processes. So there's two directories, key slots and PCRs. So I showed this briefly on my earlier slide. So when you create key pairs, this thing has a limited number of slots. You have to actually load this wrapped blob into the TPM to be able to use it. And it has 10 slots, and you can see there are 10 slots if you actually go in there. No permissions means no keys are loaded in that slot. And it has 24 of these platform configuration registers, the things that you use for storing those SHA-1 hashes. So what I will do is, Okay, so again, this is very stereotypical. This is like a textbook experiment or textbook use of this thing, is that assume that these registers or the hashes contain within. Right now, they should not contain anything. Assume that they represent the state of your system. So they're all empty. I mean, they're some are -1, but you can't actually use them. Assume that they represent the state of your system. Like you measured your kernel, you measured a whole bunch of stuff, and the hashes actually represent that. So what you can do with the TPM is, what you can do here is that you can encrypt a bunch of stuff. And you can say that I'm encrypting this, but this can only be decrypted on this TPM if the hashes within match at the time of decryption, they match what they were at the time of encryption. So something like this, that I can say, so I'm saying, sealed, this thing is called sealing. Seal this thing, bind it to this register number, and so I have this blob here, this is armored. And, well, you can try to unseal it. It works. Now, what this extend PCR does is, so let's look at those registers again. So let me extend a PCR, which means that I'm generating an event or something. I'm just saying that here's the event, it's a string. And extended PCR number. So there's a hash in there now. And let me try to unseal it again. So it says wrong PCR value. What can you do with it? Well, Microsoft is doing the BitLocker, is that what it's called? Some kind of drive encryption thing. We can actually do that on OS X too, in more ways than one. The firewall talk that we had, it gave me some ideas, but even if you don't use firewall, OS X has another. See, they're very nice with filters. They don't give you APIs, but they give you a lot of filters. So one thing Apple gives you is a block storage filter, which means that you can write a kernel extension and you can sit atop a block device, whether real or virtual. And then you get to see everything that passes through. So you get to possibly rewrite the contents of every block as it passes through. So you could use this with that to create your own disk image framework if you want. That thing is quite well supported. The other thing you could do with this is, again, it's kind of a stereotypical example. So if you go, let's see if I have network here. Okay, so this is how I log in. If you go in my .sh directory, you will see that I have this thing called authorized keys. What does it contain? It contains what you would expect, except that in this case, it's not like a software-generated public key. It's something that this key pair was actually created inside the TPM. The private key was spitted out as a blob. Mess with my terminal. So what if, okay, so here's a trivial implementation of RSA sign from OpenSSL. All it does is, instead of using what it would do in software, it just offloads that work to the TPM. So when the key exchange is being done during the initial SSH handshake, so what I'll do is I will interpose this, I'll LD preload equivalent this library in my SSH connection here. And So all this does is if I give it an argument, so what is the argument? So the argument is that you have to load this key into the TPM first. So I have a key handle, and then I can say login. So it logs in, and well, within reasonable limits, this login is quite secure because, well, in a way it couldn't have been made other than from this machine because this RSS signature couldn't have worked except inside this TPM. At least that's the idea. And no, there's no secret here. I mean, there's no like, oh, but it breaks under those circumstances. It's actually quite nice. So, where's my mouse? Okay, so maybe I'm giving the impression here that I really like this and there's nothing wrong with these technologies and all the privacy concerns are unfounded. Well, that's not really the case because it looked like Palladium would disappear and Microsoft would, you know, they just thought it's a bad idea. It was really badly received. But so Intel has La Grande. I think I've heard people here talk about it, so I'm assuming that you know what La Grande is. The TPM is just one of the components in La Grande. I mean, it actually extends a lot of stuff. So if this is your PC platform today, with La Grande, it's a lot. In fact, it really is trying to create this reference monitor thing that I mentioned earlier, because what will happen here is that you get essentially ring -1, and you run some kind of like this tiny hypervisor kernel inside this ring -1, and so a common argument today is that, well, what are you going to do if if iTunes DRM? You're eventually going to play some audio and it's going to go through your sound card. I can always capture it in flight. Or keystrokes, I can always log your keystrokes. So no matter how you tighten something, eventually I'm going to capture it. So this thing's goal is to make the impossible really hard. And they're doing some crazy things, like you will need this special USB keyboard, which, so Windows XP runs as it would. This hypervisor runs in ring -1. If there's a super secure app which runs in, like its own virtual machine, and the virtual machine is secured using the TPM, and so is the graphics card. I mean, so is the output and the input. And the keyboard will actually negotiate a key with the software, and the hypervisor will assist in this. I mean, who will program for this and why? Well, let's see. But Microsoft, so every time it looks like they're going to use it and it's just around the corner, they back off a little bit. So this is the so-called NGSCB. And I think it's a bad idea. I think it's simply a bad idea because it's really hard to program for. It's going to stultify innovation in the sense that, like, when you use applications, you want to use applications that people like to write. You don't want to use applications that are pain to write, because then most of my processing is going towards these applications and antivirus and this and that. But anyway, so these are just some random thoughts. I found this somewhere, and I think we are out of time. Do I have time to show you the demo I mentioned? Okay, so a quick rundown of that, the demo I mentioned, because since we've been talking about these mock interfaces and VM and processes. So, like I said, and the point of mock is that most things are IPC based. You want to allocate some memory. When you do a malloc, malloc eventually results in mock IPC, which says, please map this memory into my address space. it can just as easily result in an IPC that says, please map this memory in that guy's address space. So like I said, there is no difference. So OS X people want to do funny things like these. Bear with me while I type my password. So something like this. I mean, it's quite stupid, but or something like this. And I really like this because, you know, this continues to work. No. But this is not the interesting part. This is hardly the interesting part, because you show this to people who write all those fantastic UIs, they're like, huh, so what? And then I have to tell them, do you realize how this was done? So well, all these transitions and all these effects, they're actually supported by the Windows Server. It's the first-class API that only Apple has access to. All these funky keynote transitions, they're also, like, there's actually an API but you can't use. Now, well, if you knew how to use this API, let's say you reverse engineered, well, you could use them, but still in your own programs. The reason is, well, implementation-wise, you first need the window ID of the window in question. The window ID is just a number, but it's just a number like a file descriptor is a number, which means that just knowing the number is not enough. You actually need these rights. So we were talking about these send rights and receive rights. So where are the rights going to come from? So really, the only way I can do this is if I am this task, which means I'm Safari. So it means it's really easy to do it in your own program, but you can't do it in other programs. So how do you do that? Well, we use our... I'll play this while we talk. Okay, so the way we do this is, we talked about threads and processes. So what I do is I can suspend a task remotely. When I say remotely, it means like you don't have to be that task, you just call a mock IPC function. And so I suspend this task, which suspends all the threads within it. Then I suspend all the threads within it, because when I resume the task, I don't want them to run. Then I select one thread. I mean, everybody is going to have at least one thread, so I just select the 0th thread, the first thread. Then I use another mock IPC function to actually suck the thread state out of this. So it lets you do that in all the registers, just in a lump sum. I stash them somewhere else. Then I use this remote memory allocation function, because memory allocation is uniform, and other process doesn't matter. So I allocate a new chunk of memory for this guy, and I move its stack pointer over there. Then, but if you're thinking that you just inject some code and it's going to work, well, actually no, because many of the library functions, they want a valid pthread context. So you can't just have a mock thread. You need all the pthread user state too. So what I do is then, and then I allocate another chunk of memory where I'm going to actually put some code in. This code does nothing but instantiates a pthread. And once I'm done with this, I have my stack set up for the pthread. I have the instruction pointer set up. Then I resume just this one thread. So if a task is suspended, all threads are suspended, regardless of their individual suspend counts. And then I resume the thread and resume the task. Only one thread is running, my thread, the one I hijacked. And then I do what I want within it. And well, how do I know? Because I have to set it back. So how do I know that it's actually done? Well, another thing you can do with mock ports is that you can ask to be notified when they die. Die means deallocated. So the argument I give to my pthread is a new mock port I created, and I'm telling the kernel, I'm blocking on this, just let me know when this dies. And the last thing the pthread does after doing all this stuff is it deallocates the port, so I know that guy is dead. Oh, and before dying, it suspends itself. Naturally, that's the death. It deallocates the port and suspends itself. Now I can do the reverse of what I just did, which means I can put everything back in, and it happens in just a second. I mean, it's no big deal. But the important point is that all this works using interfaces. So all this uses functionality that is a first-class API in macOS 10, so it's not really subverting the system as such. I guess that's all I have. It's been a miscellaneous talk. I hope you found it useful. Thank you. Any questions, please?
Yeah. Is off. There are two specific problems regarding the TPM in Apple hardware. First, it's a common IBM misinformation strategy to say TPM is a neutral part of hardware. If you take a look at the work, for instance, from Ron Rivest, it's very clear. TPM is a building block which is problematic by design. We don't have the control about our own keys. We give away the control for our keys. Especially, we have another problem. We have attestation over the network. So a provider can check your computer without your knowledge. And the deep problem with Apple is that Apple didn't follow the data protection rules of the Trusted Computing Group. The Apple TPM hardware chip is activated. So my question is, why do you do here this information campaign?
No, the Apple TPM chip was not activated.
It was activated.
When?
In the first iBooks, second generation, it was invented. I have spoken with Seth Schön from the EFF. You could inform you, please.
No, so how do you know it was activated? I mean, without a driver, how do you tell?
It's activated in a sense, following the definition of the Trusted Computing Group of activated. Please read the standard to be informed. It's activated. Usually it was best practice for data protection that the chip is not activated, and in the Apple Mac hardware it has been activated.
No, it ships. I mean, if by activated you mean that you can see it on the LPC bus and you can send commands to it. That is expected. That's what you want.
That it's best practice for the Trusted Computing Group that the user has to activate the chip, and it was automatically activated, which has been presented by EFF, said Schön. Apple has violated the data protection best practice of Trusted Computing Group.
No, I think there's some confusion here because, okay, so one of the things you need to do with the TPM, so let's say you want to take ownership. Ownership means you want to set your own password. Then you have to establish what's known as physical presence, which means that you can't do it over the network. You have to be here. You have to press some vendor-specific keys, like it's the function key in IBM ThinkPads. And then you go into the BIOS and then you say clear the TPM and then I'm setting a new password. Apple doesn't even have that. So
Apple has no access for the TPM chip for the user point. There is no support, so IBM makes better privacy protection treatment than Apple.
I never said. That is the whole point of this talk, that Apple is not doing anything with the TPM. It's just sitting on the LPC bus. That doesn't make it good or bad. It's just a fact.
It sits there and it can be used, for instance, to produce digital registration management for Disney pictures.
But Apple can't do that.
Yeah, they can do it. You misinformation.
No, but that's not how the chip works. How is Apple going to own the chip? Because once they ship the machine...
They can control what hardware you have over desktop, over network checking of your computer system. Attestation. Please inform you. Please read the standard.
No, this is incorrect.
It is not incorrect.
No, so one of the things is that this physical presence thing I said, the point of physical presence is that no software should be able to reset the chip or like put its own password after you owned it. So to begin with, I just showed you how the thing worked. I didn't show you how I actually own the chip. So the owning process is you establish physical presence. Apple doesn't have physical presence. So in cases where there's no physical presence just means that at boot time, the BIOS actually identifies the chip. The BIOS supports showing the user a prompt and saying, okay, now own this chip. And then the BIOS sets a flag in the TPM which disables it from being able to reset from software. So here, Apple doesn't even support it in EFI, which means you can actually boot into OS X, and I can say, I want to reset the chip. And since that flag is not set, it will let me reset it from software, which is actually not allowed in a real implementation of TPM. But is it reset and owned? No. I will require a few reboots, and I'll have to do I have to power cycle the TPM. I mean, that's how it works. That's by design. So Apple can't like smuggle in, and I'm not talking for Apple or I'm not trying to defend them. I'm just saying it's technically not feasible for Apple to ship something unless they actually do a Trojan horse that here's a new funky iTunes update and do this and do that. And even then, the TPM is on your machine. If you find out, and someone will find out, you can just turn it off. So TPM is as much a building block of all kinds of DRM systems as is the computer. So you can use it for good or evil. It's not.
I have a question.
Yes?
Two things. I noticed that you have a proc file system working on your Mac. Does that mean you finally got it to stop kernel panicking on your box?
Oh, right. Yeah, good you asked, because I was feeling that nobody asked I had a proc file system going there. Yes, there's a proc file system, and I hope to release it soon.
Excellent. I'm glad that. The second thing is there anything on, I have a MacBook Pro, and I haven't messed with, I don't have the proc file system. I didn't know that it was fixed. Is there anything that's stopping Apple from releasing an update that will enable my TPM chip, since I've done nothing with it, and use it against me in a way that I don't like?
Well, no, see, the TPM by itself...
But the question is there anything stopping Apple from doing that?
Okay. The most they could do is...
It's a yes or no question.
The most no, I will tell you the most what they could do. The most they could do is to trick you into making them the owner. And
so the answer is yes?
No, but even then, once you found out, you could. But this is really. The
answer is yes, right? They can do that. They can own my machine because I don't have any interface for initializing the device in the first place. Therefore, they can own it through an update. They're cryptographically signed. They can do that. And if I want a security update, it's very possible that I'll have to apply their DRM stuff.
No, but see, what is the point of the DRM if you can turn it off?
What stops Apple from doing that? Nothing. Nothing. Except you trust them, and I don't.
No, okay. Yeah, so we're out of time, and if people want to talk, we can meet outside or here.